It's a great pleasure to introduce him with his presentation, Electron-Based Flash Measurement and Commissioning, the Shop Experience. Please go ahead, Dr. Francois.
Thank you very much, Doctor. Thank you for the introduction, and thank you to the organizer for the invitation. So the title of the talk should say the experience so far, as it is very much a work in progress that I'm presenting here today. This work is also a group effort, and the contributing physicists are listed on this title slide. So I have to disclose that we have a collaboration agreement with INTRAOP to access the Mobetron design for Monte Carlo modeling. So I will give an overview of the Mobetron version that we have. Yes, I will give an overview of the Mobetron version that we have at shown here and discuss very briefly the UHDR applications for our Mobetron. I will then describe the beginning of our journey into flash beam measurements by showing our detector validation measurements in hopes to achieve one day a complete commissioning of our UHDR beams of this machine. So our radiation oncology is a multi-vendor environment with a total of 10 LINACs, including a mix of Elekta machines, Varian, and Accuray LINACs as well. We also have a large brachy operation with 2 HDR projectors, and we do LDR as well. And in 2018, we started the acquisition process to get an intraoperative electron LINAC. This acquisition was delayed, luckily, at the end, because it allowed us to be one of the first group to receive the new 3rd generation of the Mobetron from INTRAOP. And it was possible at the time to upgrade it to get the UHID option on the machine. All right, so we eventually received the first Mobetron in Canada, and our first conventional IORT breast patient was treated at the beginning of 2021. The Mobetron is a LINAC that is built for IOERT at the base, consisting of a mobile LINAC and a treatment console, allowing to deliver 3 conventional electron energies, 6, 9, and 12 MeV, at a regular dose rate of 10 gray per minute at Dmax. The virtual source is SSD as a SSD of 50 centimeter. It has an automatic self-docking system, which saves quite a bit of time in the OR. That's a nice option on that model. As for the UHDR option, we received a second dedicated treatment console, which is not yet for clinical use. This is the way INTRAOP separates the conventional and the UHDR delivery. This is basically to avoid flash beam irradiation being done by mistake. So indeed, console 1 is the regular console of the previous Mobetron generations, allowing selection of conventional energy, 6, 9, and 12, and also allow us to select MUs, enter MUs. This is to be used with the 60 or so conventional applicators that are 30 cm long and that have a range of diameters from 3 to 10 centimeters that also come in bevel version at various angles. The second console is for the UHDR, for the ultra high dose rate beams. It allows give us 2 UHDR energy, 6 and 9 MeV, and 1 conventional 9 MeV energy as well that can be produced using that console. It comes with also for the UHDR, it comes with ILTEM or ABS plastic applicators of length 30 cm or 20 cm. And they are provided with variable collimator inserts. I will show a picture of that in the next slide. So we see the conventional console that some of you may know. And the new UHDR console, as you see, there is red warnings a bit everywhere, not for clinical use, and there's a big red sign at the on the screen itself, also saying careful, ultra high dose rate. So the interface allow us to only enter a number of pulses. This is the only thing that we can select. We have to go to a second device, which is placed on top of the console, to select the pulse repetition frequency from 5 to 90 Hertz. And we can also change the pulse width between 0.5 to 4 microseconds. So in UHDR mode, we can typically have 1.3 and 1.5 gray per pulse at 50 cm SSD for a 10 cm collimation, either for 9, respectively for 9 and 9 MeV at Zmax, Dmax. So here are some pictures of the applicators, the conventional one on the left and the new ones, the plastic ones on the right, and we see the inserts to vary the size of the collimation. So what differentiates the UHDR mode from the conventional mode is that the electron beam is boosted to the maximum power. The solid state modulator in the machine limits the use in UHDR mode to only 6 and 9 MeV energy. The monitor chamber saturates, so we can't monitor, we can only count pulses. That affect the dose rates. So at this moment, only 5 centers around the world use this version of the Mobetron with UHDR console, and I've listed them all here. So UHDR beams are not yet approved by the regulatory authorities, so this will have to be validated, accredited in the future. At least in Canada, we plan to go through that process with Health Canada at some point. But among our research goals listed here, I will only discuss the evaluation of some detectors that we did in our journey towards understanding the beam dosimetry of these UHDR beams. So we need to know what we want to use the machine for in order to best commission our beams. Of course, in terms of future clinical trials, there are interests to do skin cancer, which needs the lower energy for the lower energy of the beam, and for possible maybe IORT sites, we would like higher energy to be a bit more penetrating. So basically, we want to have the largest range possible, having only 2 energies. So we want as low as possible energy for the 6 MeV and as high as possible for the 9 MeV. So we have to figure out how to deliver X gray using N pulses. We can vary number of pulses, the pulse width and the SSD, as well as the applicator diameters. That last parameter is actually important because the output factor may vary up to 50%. We need to be in the flash regime, of course. All these factors have to be taken into consideration as they will vary the dose we deliver at Dmax. Typically, one could use 4 microsecond pulses, so the larger pulse width, and obtain about 2 gray per pulse at a Dmax for an SSD of 50 cm. So if we use pulse repetition frequency of 60 Hertz, we would get actually 120 gray per second, which is 3 orders of magnitude larger than conventional beams. So a treatment would typically be composed of only a few pulses, say 10 to 15 typically. So the approach for detector validation, as there is no primary standard and code of practice yet, is to use a combination of detectors that use different prediction principles. We aim to go from passive dosimeters to active dosimeters that will allow real-time dose measurements. Some detectors can be used to monitor the beam looking at the relative output. Obviously, we would like to be better than 3%, but from literature, 3% seems a fair relative agreement, considering there's no code of practice yet. Hopefully, there are some groups working on guideline now For example, the Ampere UHD pulse and TG359 from APM, and many others. So we use passive detectors, mainly FIM for now, as it does not have dose rate dependency. FIM is used as our ground truth for now, as we know there is no saturation effect. We use clinical electron dosimeters such as PTW Advanced Marcus and microdiamond for acceptance test, as I will explain later. The hypersyn plastic scintillating detector is used as a real-time detector, and it does not suffer from saturation effects. The plastic scintillating detector is calibrated on a conventional LINAC using parameters that were specifically chosen to cover a high dynamic range and dose rate. We are still characterizing the response of the plastic scintillator to large cumulative flash radiation dose. There is an expected decrease in output of the scintillator with cumulative dose. Based on these results, we will have a better understanding on how often we need to recalibrate this detector. Alanine and graphite calorimeter will be evaluated in the near future in collaboration with NRC. We aim to perform a multi-way comparison of all detector results at the end. Note that the active dosimeters can also be used in a water tank, which is something we need. So, and there is beam monitoring. This is one big issue. So for the moment, we use a large X-thread A17 located in the branch along tail of the beam. So we place it under a stack of solid water as shown on the left picture. It can give us a relative output, but to relate to a beam fluence, we need to replace it at the exact same location from irradiation to irradiation. So it's very difficult to be consistent that way. So it's not a very robust approach and clearly is not a solution for the long term. A better approach is to use something as a toroid, either at the exit of the accelerator or in the head to measure the fluence of the beam. The toroid measures the fluence of particle passing through its center without affecting the beam itself. The one we are testing from NRC is not incorporated into the Mobetron, so we placed it at the exit of the beam on a very elaborate setup made out of a pile of styrofoam, as you see on the middle picture. This will be used for pulse counting and individual pulse measurements, including looking at the shape on individual pulses. In the meantime, to our knowledge, Introp is working on their own toroid design that will eventually be incorporated into the Mobetron head. That will certainly help. Another option to characterize dose distribution per pulse would be to use Cherenkov dosimeter. This could be done in water, but not for in vivo. This paper from the Dartmouth group described their approach. It's a very interesting approach as well. Another option that I've not illustrated here is to collect charges generated by the passage of the electron beam through a conducting foil, something as a Faraday cup, basically. So for the acceptance of the machine in the UHDR mode, IntraUp suggests the use of electron clinical dosimeter being used below the flash regime, so at less than 1 gray per pulse to avoid saturation, especially, for example, with our advanced Marcus chamber. So for our depth dose in water, we use 50 cm SSD, pulse repetition frequency of 30, and pulse width of 1.2 microseconds. And obviously we acquired in step and shoot mode because we need to move the Marcus from a different position. So in the air measurements, we shown, we didn't use collimator. This is shown in the picture there at the center at extended SSD. And we measured reproducibility and linearity. The acceptance test required the dose rate to be higher than 50 gray per second, so we use about 20 gray per second. We validated the dose measured with our chamber with fin measurements to ensure that there was no saturation effect on the chamber. Continuing on the acceptance test requirements, here are some results with the advanced Marcus chamber. We observed a strong linearity between the charge collected and the number of pulses. The reproducibility under these conditions for 10 pulses repeated 5 times yield errors of 0.5 and 0.9% for 6 and 9 MeV respectively. We have noticed that reproducibility is worse when we use a low number of pulses, like below 1 to 3 pulses or so. Output per pulse tend to decrease with increasing number of pulses. The trend seems to be up to a few percent. All these measurements were taken under acceptance beam condition, and then we have to reevaluate all of these in flash condition with other detectors. We also need to better investigate the linearity with pulse width. Before commissioning, we will ask the intra-op engineer to tune the parameters to our needs, which means, like I said before, we want the 6 MeV UHDR energy as low as possible to treat skin. So more dose per pulse, and the 9 MeV UHDR energy as high as possible for IORT sites eventually. The idea is to have a larger spread of energy as we only have 2 UHDR energies. So the 9 MeV conventional energy, we would like the PDD of this energy to match the 9 MeV UHDR. We will then measure PDD profiles, output factor, energy stability, linearity, pulse width, pulse repetition, frequency dependence. As for beam monitoring, as mentioned before, we need something permanent. The toroid is most likely the best solution. So calibrating the toroid with dose from a reliable dosimeter would allow us to use it as a surrogate to monitor to a monitor chamber. So PDD measurements now. So on the left image is an example of a setup to measure PDD. You see the applicator attached to the treatment head. The plastic centiator or the film could be placed at different depth in solid water. The films are placed perpendicular to the beam, of course, on that setup. For film, we can have one place at Dmax and the other place at different depths to obtain our PDD measurements in one irradiation. For the plastic centiator detector, we need to use a relative output from the A17 chamber to normalize each measurement to obtain the PDD. On the right image, the film is placed parallel to the beam to allow us to measure the full PDD in a single film, on a single film, and compared to the other single point approach from the left setup. Again, the idea is to have redundant measurements to gain confidence in our detectors and setup. The normalization of the A17 reading is in general less than 2% of the correction. These are the results on the left side's top measurements, so multiple depth measurements in solid water for 6 and 9 UHDR at the PRF of 60 Hertz, pulse width of 4 microseconds, and number of pulses equals to 5. This gives a relatively good agreement between the film and the plastic centiator in solid water. The agreement is slightly better for 6 than 9 MeV. In terms of energy, we can see that the agreement between film and plastic centiator is within 1 millimeter in the high gradient region, around R50 actually. Now that we are convinced that the plastic centiator can provide reliable results, we will redo PDD measurements with the plastic centiator in water. We expect to see small deviation between solid water and water. And we will also use the A17 to normalize the plastic centiator reading until we can get our hands on a reliable toroid. The next step is to measure the dose for a reference condition using a larger applicator, 10 centimeter diameter at SSD 50 at Dmax. Dmax being 1.2 and 1.8 centimeter depth for 6 and 9 MeV respectively. So we use film and plastic centiator to do this. We have to choose the number of pulses to perform our reference dosimetry. We decided to use 5 pulses. It is a good range for our Galvtronic EBT XD film. So our range is around 5 to 20 gray because we calibrated in reflection mode. So it's close to potential treatment dose, around 10 gray, but we would like to reevaluate this with more pulses as well. So our FIM would have to be recalibrated in transmission mode to have a better calibration curve. So we obtain a general agreement within 1% between film and plastic scintillator for both energy, which is pretty good. As you can see, the dose.
Thank you.
As you can see, the dose per pulse for the two energies are not equivalent. The dose per pulse is slightly higher for 9 MeV, 5 to 10% high. Therefore, at this point, knowing that you want to deliver a certain prescription dose, you can calculate the number of pulses required for a specific prescription dose. And one could also play with the other parameters such as pulse width, SSD, and collimation to adjust the dose. It is desirable to have a small enough dose per pulse to offer finer control on the delivered dose. So after the energy will be tuned, we plan to measure all these parameters with the scintillating plastic detectors, as we have shown it to be appropriate for dosimetry. It is important to evaluate the day-to-day variation of the output and energy, especially investigating possible drifting with time. We are a center that moves our Mobetron quite a bit. We go from our radiation oncology department in the 4th basement to the 4th floor where the OR is. So the machine goes through a bunch of corridors and elevators. So it's a little bit of a bumpy ride. So we need to have a strong way to do our daily QA check. And we aim to use a similar approach that we do with our chamber for conventional IORT beams, basically measuring the 2 points output. We are currently doing Monte Carlo modeling of our Mobetron head. We use GL4 and tuning beam parameters, energy spectrum and spot size to measure PDD and output measurement factor. So this is a work in progress, obviously. It was done by others in the past. For example, this group in Belgium with an old version of the Mobetron. There are, of course, several interesting applications once we will have a good model. So conclusions, there is a lot more to do to complete this commissioning.